Hello dear audiences, welcome to the episode 10 of Probability and Statistics for Engineers, and this is Mohammad Momenzadeh, the presenter of this lecture. So previously we discussed about the random variables, and we also talk about the probability distribution function for a given cases, and we calculate and construct the probability distribution functions table, and we discussed about the several examples. Right now we want to talk about the cumulative distribution function as well and the remaining parts. So this is our topics in this course that we want to cover it today, and briefly we will discuss about the integrals, and we will use the application of an integral to calculate the probability distribution function for continuous cases. So let us take a look at the first slide today. So this is a cumulative distribution, and we want to talk about that cumulative distribution function indeed. So as you can see over here, we have a definition of cumulative distribution. The cumulative distribution that is denoted by capital F instead of the lowercase f of a discrete random variable x with probability distribution of fx if this is the situation for the function, for the given function. Means that if you have a probability distribution function, the addition of a probability of the previous values determine the probability distribution function. For instance, in this case we can make one example, and in that example you can see the cases that we have it. For example, over here, if we have a table of a distribution for a given random variable, for example over here, let us denote the first line by x. The random variable is given by capital X equal to xi. Let us assume that we have the value as following: -2, 1, 3, 4, and 5. These are the values for the random variable. As I said it before, this assigning the value is totally on our hand. Means that we can determine any values that we wanted, and we determine the probability distribution function by the small f, and we put the index of capital X at the bottom to determine the probability distribution function, and this value determine the probability of that point. Means that this f at the point xi is as the same as the probability of x is equal to xi. So for these values we can put the probability of x at the point xi. For example, in this type of the example, we can have this probability 0.1 for the first point, 0.2 for the second one, and 0.1 again for the point 3. Let us assume that is equal to this value and 0.3 over here. So since the addition of the probability should be equal to 1, we have 0.7 in a total, so we put 0.3 for the last value. So right now, if I want to construct the table of a distribution, construct the graph of a function over here, means that we can sketch even the graph of a function. So the graph of this function can be considered as a value for the x for different values that we have it over there. If the x line determine the random variable, means that we put the x equal to xi for the horizontal line, x equal to xi, I put it over here as a x line, and the probability values, which is the value of the f of x, is denoted in a y line or the vertical line over here. So for different values we can put these things over there. For avoiding the problem of 0, I just put a gap over here at the beginning of that x line or horizontal line to show that it's not necessarily started from 0. So I start the value from -2, then the next value that I can consider it over here, assume that it's 1, then 3, then 4, and then 5. So for these values we have the corresponding probabilities, and for each probability I can denote the values over here. 0.1, assume that it's like this. 0.2 is 2 times of the previous one. 0.1 again for the point 3, and 0.3, which is here, and 0.3 again that we have it for the 0.5. So this is a graph of the distribution function. Right now, when we discuss about the capital F, the cumulative distribution, we should calculate all the probability that we have it for the previous value. Means that f of x, if I denote that capital F and put the index of capital X over there at the point X, should be calculated as follow. Means that I can put one function like this and write it over here. For the previous value of -2 over there, if the value is before -2, the addition of all probability up to the point -2 is equal to 0. Always the cumulative distribution should be started for the discrete case especially, should be started by 0. So it's cover all x's that the x is less than -2. So for the value that we have it for x less than -2, we have no probability over here. If we cover it, if assume that we have a machine or a car that move from -infinity, assume that we have a car over here, that the car moved from -infinity. Its travel or journey from -infinity. If it started from -infinity up to the point that we reach to -2, there is no probability, so there is no actually cases over there. But if that machine travel from -2 and pass -2, means that we have a probability of 0.1 based on a probability distribution function. Up to the point 1, we have only one probability, which is -2. So the probability, the addition of the probability of that point will be 0.1 for x less than 1. So up to the point 1, we have no probability except the at the point -2, which the probability is 0.1. But when we reach to point to the point 1, then we have two probability, and from point 1 up to the point 3 means that up to this point, up to this value, we have the addition of two probability. One of them belongs to -2, one of them belongs to 1. So addition of these two probability means that 0.1 and 0.2 together will be 0.3. So I should calculate the value of them up to the point 0.3. For x, let me just put the restriction over here from -2, then we should have these cases. From 1, as I said it, when I start our journey from a point 1 up to the point 3, but not reaching to the point 3, the probability of 3 cases should be added. So we have 3 cases over here, 0.1, 0.2, and 0.1 again. So the probability of that case will be 0.4 indeed. So we have 0.4 here. So for the next case, as you can see over here, when we reach to the point 3, and from a point 3 to the point 4 means that for this gap, if we pass the 3, so we have 3 probability over there, so we should add them together, 0.1, 0.2, and 0.1. Again, it's gonna be 0.4, and it's determined the cumulative probability for x between 3 and 4. 3 included, but the 4 is excluded over there. So between 3 and 4, we have this case. And again, if we reach to the point 4 up to traveling to the point 5, means that for this journey, then you should add the probability of 0.3 for the previous value. So we have 0.7 over here. 0.7 for x range between the point 4, the 4 included, but the 5 is not. And after the point 5, if I travel and pass the point 5 and x will be greater than equal to 5, the value of this probability will be equal to 1. And always for any probability after 1 point, we should have the cumulative probability of 1, because the addition of all probability should be equal to 1. Let us calculate one of them by using a formula as well. For example, if I want to calculate the f of x at the point, for example, let us consider 4.2. Of course, we can use that table and that function to calculate the capital F at the point 4.2. It belongs to this class, means that x is between 4 and 5, and we can calculate it. But based on a formula, when we have the f of x of 4.2, means that I'm looking for the probability of x is less than equal to 4.2, and of course these points cover some values over here, means that it's as the same as the probability of x equal to -2, because that x is less than actually 4.2. There is the another value that we have it as well, which is probability of x equal to 1, because it's less than 4.2, and also we have the probability of x equal to 3, because 3 also is less than 4.2, and also 4 by itself will be inside of this value, means that it's plus probability of x equal to 4. So by the other words, it's equal to the probability summation of some probabilities over here. As you can see, it's a summation of these probabilities, and of course the value will be 0.7, but we can summarize this summation as a summation of probability of x equal to xi, where xi is a value less than the given point, means that this xi should be less than equal to 4.2, less than equal to 4.2, and the addition of them give us the 0.7. So by the another word, this cumulative probability determine the values, the addition, the summation of the values that we have it in the previous things, means that if you consider the cumulative distribution function as a machine that start its journey from -infinity up to the given point, then all type of the probability previous to that one should be added and calculated for that values of the probability. I hope that you understand the concept of the cumulative probability function. So before that we're going forward, it's not a bad idea to take a look and review on a concept of the integral. When we discuss about the integral, indeed it's better to keep it in your mind that the integral is the summation of a continuous values. Continuous value over here are added together to calculate it by the integral. For example, if we have a function of y equal to f of x here, if we have a function like this, y equal to f of x, and we want to calculate the integral of f of x, we have the integral. We use this notation for the integral. It looks like a sketched S. It's a beginning of the word summation. If you just consider the integral symbol determine the sum of the values, and this S is a stretch over here, and we have the integral. So integral of f of x dx, we use this notation to determine the integral. So if we have the integral of f of x and we have a boundary over here limited for the integral between a and b, it means that we want to calculate the area under the curve of y equal to fx between the points x equal to a. This is x equal to a. If you just take a look on it, this is x equal to a and this is x equal to b. Means that we restrict ourselves between x equal to a and x equal to b. Let me just put it here, x equal to a and x equal to b, and positive side of the x line. So this area that I shaded by the yellow colors are is the area that we will calculate it by the integral of f of x dx between a and b. And as you can see, it's as the same as summation of some small rectangles over here. We have a shape like a rectangles over here. This shape, for example, over here, it's for calculating the area under the curve. We just divide that area to small parts, and then by adding these small parts we can calculate the total area. And as you can see over here, the height of this one, the length of this rectangle, if we consider it as a rectangle, then the height of this rectangle is f at the point xi. We can consider the point xi as a point between a and b, and we multiply it by delta x. So it's a summation of f of x I delta x. This is the value of the rectangle. It means that this is the area of rectangle. This rectangle by itself has the area of this value. This give you the length and this give you the weight over here. So we have L and W. If you remember that to calculate the area of one rectangle, if there is a rectangle and one side of this rectangle has a length of delta x over here, so we have a delta x over here, and the other side of that rectangle has a length of f of xi. So this f of xi is the length of that one, f of xi, and we multiply these two values to calculate the area for that rectangle. Let us put the value over here. So this is the area over here, and by adding all of these values together we will get the area under the curve. So it's important to understand these things to connect this concept to the continuous probability distribution function. Indeed, for calculating the probability over here, we will add small values together to find the function indeed. So let us take a look at the definition of continuous probability function. So let us return back to our discussion, and I want to tell you that to be not worry about the integral. Most of the students, when they face with the integral, they get worried, but mainly we need these two formula only to calculate the integrals of the probability. I just want to ask you, if you forget the integrals formula, you can return back to the calculus 1 and review the integral parts. But mainly we use these two formula. The integral of x to the power of n dx is equal to x to the power of n plus 1 over n plus 1 plus c, and the integral of x to the power of minus 1 is ln x plus c, and also the integral of e to the power of ax equal to 1 over a e to the power of ax. This is the fundamental theorem of the calculus, and by using this formula you can calculate the area under the curve for the given function. If it's a polynomial like the expression in the first example, simply the coefficient like 4 over here and 2 over here is coming out from the integral, and you can write it as a 4 and then add 1 to the exponent, means that the exponent here is 3. So we have x to the power of 4 and we divide it with the same number, means that with 4. And we do the same for the remaining parts as well. For e to the power of half x, we have 2, which is inverse of half, e to the power of half x plus c. And it's an important formula. It's a fundamental theorem of the calculus that you can calculate the finite integral by using the formula of the integral over here. So it's easy to use them. I hope that you can review the calculus 1 and understand how to calculate the integral. So let us return back to the discussion. We have the continuous probability distribution here, and over here we have 3 conditions to call a function a continuous probability distribution. If you just remember the discrete cases, for the discrete case we said that f of x or the given function should be positive. Here we have the same thing. Again, I want to emphasize that the value of the function should be positive, means that the curve of the function should be upper the horizontal line. It cannot go down to the horizontal line. The second condition is as the same as the addition formula that we had it. For the discrete case, we said that the summation of fx where x taken from the sample space or for all x's that is belonging to the random variable, the value of the summation is equal to 1. And instead of the summation over here, as I said it, we use the integral from minus infinity to plus infinity. Over here, all the values under the curve should be equal to 1. The area under the curve from minus infinity to plus infinity should be equal to 1. And as I said it before, the integral is the addition of some values, but over here the integral is used for the continuous value. For the discrete we have these cases. And the third condition that we have it over here is as the same as the third condition that we had it for the discrete cases. Indeed, we said that the probability, the f of x, the value of f at the point x, is as the same as the probability of a function, probability of x, random variable x, is equal to small x. Over here, instead of talking about one specific point, we calculate the probability of x between a and b. Means that if x belonging to some interval, then the integral of fx between this interval determine the probability. So of course, again, I want to emphasize about the situation that the probability of one specific value should be equal to 0, since probability of x equal to a. Over here, if we have a continuous random variable, probability of x is equal to a is as the same as saying that the it's as the same as saying that the probability of x is a range between a and a. And if both sides of these limits are the same points like a, then the result will be integral of a up to a. The integral of a up to a of f of x. And if we find the preliminary function for that value, means that if we find the integral of f of x and we denote it by capital F, as we did it for the calculus, f of x between a and a, then the result of that integral will be f of a, the capital F at the point a, minus capital F at the point a, and the result is 0. So I want to emphasize it again that the probability of one specific point for the continuous random variable always is equal to 0. So the another thing is the cumulative distribution of fx that we denoted by capital F. Previously we used the summation to determine that probability, but over here instead of the summation we have the integral. Indeed, if we consider the following cases, let me just sketch it here. So I sketched the probability distribution function here. As we have it in the conditions, all the values are positive, means that it's upper the horizontal line, it's over here. And also the integral under the curve should be 1, means that the area under the curve should be equal to 1. Over here, if you calculate the integral from minus infinity to plus infinity, it should be equal to 1. And right now, if I want to calculate the cumulative probability, for example, if I want to calculate the probability, the capital F at the point x, which is given over here, then I should calculate the area under the curve previously to this point, means that this green part should be calculated. And this green part determines the value of capital F. Let us take a look at an example and see that how it's working for a given example. Let me just give you the example. So if you remember from the previous lecture, we said that for the continuous random variable, we said that there is a machine or a computer that select a number randomly between 0 and 10, and this number could be a pi, could be any real valued numbers. So if we add one more condition that the possibility of getting any number are the same, means that the possibility of getting, for example, the number pi over here is as the same as the possibility of selecting the number like 7 over here, then we have the uniform distribution over here, means that the possibility of getting pi and the possibility of getting 7 are as the same. I'm looking for the probability distribution function for this case. So over here, if you remember the condition for the probability distribution function, we had 3 conditions indeed, and with that 3 conditions we can determine the function of the probability. So the first condition was about the positivity of the function, means that f of x should be positive for all given values. So we should care about these things. The second one, which is important and can determine the probability distribution function, is about the integral that from minus infinity to plus infinity. If I take the integral of f of x, then the value of that function should be equal to 1. I will use this concept to calculate the probability over here. So indeed, if I take the integral from minus infinity up to plus infinity of a given function, where the distribution is uniform, means that the probability of getting pi is as the same as probability of getting 7, means that the location of them is not important and the probability of them should be the same. So the value of the function should be constant, means that it's not related to the x. It's as the same for any value over here. So I should write that the f of x is equal to some constant number. Right now, how can I calculate this constant number? To calculate this constant number, I just divide the integral to many parts. From minus infinity up to 0, first I should calculate that constant value, which is k dx, plus I divide it between 0 up to 10 for that value, I mean for the k constant numbers, and then at the end I just extend this interval to 10 up to infinity, 10 up to infinity for that value k dx. So because the probability of getting that numbers out of this interval is 0, means that this k over here is equal to 0 and this value over here is equal to 0. So these two integrals will be removed and we don't have any value on the outside of this interval. So simply we have one integral and this integral is defined only for the value between 0 up to 10, means that it's going to be 0 up to 10 of k dx. It was better from very beginning to use f of x instead of the k, means that it was better to say that it's f of x, but as you can see, the value of f of x outside of this interval is equal to 0, and inside of this integral it's a constant value, which is k. And of course this k should be positive. The integral of k is a constant number, will be k times x, and I should determine the integral between the value of 0 up to 10. If I replace x by the upper limit, means that 10, then I have 10k, and if I replace it by the lower case, it's gonna be 0. So this value should be equal to 1, and then I found out that the k should be equal to 1 over 10 or 0.1. So right now I determine the f of x, means that f of x, or the function of the distribution at the point x, should be equal to 0.1, or the constant value over there, 0.1, for the value between 0 up to 10, for x between 0 up to 10, and for the other value it was equal to 10, so the 0. So we have 0 for the others as well. So this is gonna be our distribution function here. For the other value it's gonna be 0. So right now if I want to calculate the probability distribution, cumulative probability distribution function, also we can do the same thing. But before that, we're going forward, let us consider the third condition and see that how this third condition works here. The third condition said that the probability of x between a up to b should be equal to the integral of that function, integral of f of x between a and b, means that integral between a and b of a function f of x determine the probability at that point. So f of x dx. Right now, let us take a look at the situation. Previously, we said that, for example, the probability of getting a number between 0 and 1 should be equal to 1 over 10. Let us see that if it's correct over here or not, because the segment between 0 and 1 determine 10 pieces over here. If we divide or split the interval between 0 up to 10 to 10 parts, 0 up to 1 will be one segment out of 10 segments that we have it, and the probability should be 1 over 10. Let us see that if it's correct or not. Means that previously by the inspiration of the situation we said it, but right now we want to calculate it. So the probability of x between 0 up to 1 is as the same as the integral of that function, means that it will be integral of that function. The function is given by 0.1 in that interval, 0.1 in an interval of 0 up to 1 of dx. And to calculate that integral, we know the integral of 0.1 is equal to 0.1 times x, 0.1 times x, and x ranging between 0 up to 1. And right now, if I replace 1 instead of the x, I have 0.1, and if I replace 0 instead of the x, I have 0. So the value of that one will be 0.1, the value that we expected before. So in the same way, we can calculate the cumulative probability distribution function as well. For this type of the thing, we should evaluate the capital F over here, or the continuous or the cumulative distribution function. So if I want to calculate f of x, the capital F of x, based on a definition, this integral, this can be calculated as the integral from minus infinity up to the given point x of the probability distribution function. Means that this is let us use t instead of the x over here to not mix it with the x variable over there. So f of t dt. So this will be the calculation of f of x. And as you can see, if the value is between the 0, then the cumulative distribution should be 0, because over here there is no value of the probability to be covered. So if I sketch the f of x, let me sketch the f of x as well to show you that what does it mean. If there is a line over here, the function f of x that we have it here is defined for the value between 0 up to 10. Between 0 up to 10, the value is 0.1. Let us consider that one as a 0.1, and this is a 0.0 up to the 0.10. I have the value of the function as follow, means that the value of the function at that points are a constant value and is equal to 0.1, and otherwise for the remaining part the value are 0, means that I should have these things. And as you can see over here, the area under the curve for this function is equal to 1, means that the area under the curve of this function is the rectangular part that is equal to 1. And as you can see over here, this height over here is 0.1, and this length over here is 10. So 10 times 0.1 is equal to 1, and this is the area under the curve. Right now I want to calculate the cumulative distribution. So if the point lays on this point over here, then the area or the probability that we have it before this point is equal to 0. Let us see that what's happened. If x is less than 0, then let us calculate the cumulative distribution over here. If I want to calculate f of x for this value, for the x that is given here, it's equal to minus infinity. It's equal to integral of minus infinity up to the point x for a function f of t dt, f of t dt, and let us put the x as well as an index over here. So as you can see, the value of the function over here is that it's located on a others point, means that it's located over here before the 0, and the value of the function over here is 0. So means that it's going to be the integral of minus infinity up to the point x
of the value which is equal to 0 dt, and the integral of 0 is a constant number, is equal to c, and if I put the minus infinity up to 0, the value will be 0 as well. So for these things, the cumulative distribution is equal to 0. However, if the value of the function, it's x between 0 up to 10, if this value is given between 0 up to 10, then let us calculate the cumulative distribution. Again, we have the same situation, means that this part is the same. We have the f of x, and f of x is equal to the integral from minus infinity up to the x. But over here, we should divide the integral to two parts. One part from minus infinity up to 0 of f of t dt, because the point is after the 0, and we have some values over there. Then I have also from 0, the integral of 0 up to the x of ft dt. Means that in this case, the integral of that function should be divided to or split to two parts, because the x is located somewhere here. So if x is located here, then as you can see, we have two parts. One part is before 0, that the integral is equal to 0. One part is after the 0, and it's equal to this area under the curve that we have it. So this length is equal to x, and this length is equal to 0.1. So by the another word, the integral that we have it over here, the integral which is the area under the curve, is as the same as 0.1 times x. Let us see that if we can get the same thing over here. So as you can see, from minus infinity up to 0, the value of ft is equal to 0. So I will put that one as a 0. But f of t at this point between 0 up to x is given by the question as a 0.1. Over here we know that the value of the function for x between 0 and 10 is 0.1. So we have the integral of 0.1, and the integral of 0.1 is equal to 0.1 t, where t is ranging between 0 up to x. And if I replace t by x, then I have 0.1 times x. So minus, if I replace it by 0, it's going to be 0. So we have, indeed, we have 0.1x for the value between 0 and 10, if x is between 0 and 10. And at the end of the day, if x is greater than 10 or greater than equal, doesn't matter. The equality is not changing anything else in continuous distribution function. So then f of x over here can be split to three parts. Means that right now the x that we have it here is located in some points over here, and all the probability that is covered from beginning up to that point should be equal to 1. But let us see that if we can get the same thing or not. So of course we have again the same thing, means that the definition is not changed. We have the same actually definition, the integral of ft, where t is ranging between minus infinity up to the point x. But over here, to calculate it, we should split it to three integral. One from minus infinity up to 0, one from 0 up to 10, from 0 up to 10, one from 10 to x, because the x is outside of 10, it's greater than 10. So from 10 up to x. These two integral from minus infinity to 0, and that part which is x is greater than 10, f of t, or the distribution function, is 0. So both of them are 0. So the only part which is remained over here is the integral between 0 up to 10. So it will be the integral from 0 up to 10 of the function, and the function at this interval is not 0, it's 0.1 dt. So the integral of that one will be 0.1 t, and that value t is ranging between 0 up to 10. So if I replace t by 10, then 10 times 0.1, it will be 0.1 times 10. So this value will be equal to 1. Minus 0 is equal to minus 0, which is equal to 1. So we calculate the cumulative distribution function over here. And if I want to just write that function as a one case over here, I can rewrite it as follow. Means that I can rewrite it over here that f, the cumulative distribution at the point x, will be equal to this value. For the value that we have it for x less than 0 is equal to 0. As I said it, you can put the equality as well over here. It's not change anything else. For the value between x between 0 up to 10, then again, if I put the equality, it's not change a lot of things. I mean, we have the same values. Don't worry about that equality over here at the continuous case. Of course, it's going to be 0.1 times x. As you can see, we calculated like that. And for x greater than 10, the value of cumulative distribution is equal to 1, as you can see over here. So we can write the situation like this over here. Let me just show one more example about the cumulative distribution function and continuous random variable. At the end of the day, let us take a look at the last example of this lecture, the example that gave us the probability distribution function fx equal to kx times 1 minus x for x between 0 and 1, and elsewhere it's going to be 0. So we can sketch the graph of this function as well. First of all, at the first part of the question, they asked to find the constant k such that the given function determine the probability distribution function. So for calculating that one, I use the condition for the probability distribution function. If you remember that at the second property, we said that the integral from minus infinity to plus infinity of f of x should be equal to f of x dx should be equal to 1. So if I want to calculate this integral, then I should divide and partitionate the space. So means that we just take the integral from minus infinity up to the point 0, and then from 0 to 1, then I should calculate it from 1 up to infinity. Indeed, we just collect the limit of the integral such a way that we can calculate the value of the probability distribution function based on that one, because elsewhere means that on the other side of the values, the value of the function is equal to 0, so the first and last integral should be equal to 0. So the first and last integral is equal to 0. Then it only needs to calculate the integral in the middle. So means that this integral is equal to integral of 0 up to 1 of the integral of the function kx times 1 minus x. And if I just multiply that expression by the bracket 1 by 1 by the parentheses 1 by 1, then I have kx minus kx squared and kx squared dx. And to calculate this polynomial, the integral of this polynomial, we just need the first formula of the integral that we discussed about it before. The integral will be k x squared over 2. The integral of x is x squared over 2 minus k times x cubed over 3, because we should add 1 to the exponent and divide it by the same number over there. And this integral should be calculated between 0 up to 1. And if I put 1 instead of the x, then I have 1 over 2k, or k over 2 minus k over 3. So k over 2 minus k over 3 will be k over 6. If you take a common divisor, then 6 will be a common divisor for them. Then we have 3k minus 2k, so 3k minus 2k, and the result will be k over 6. And if this value is equal to 1, then we can find the k as well. At the beginning we said that it should be equal to 1. So by this expression, by this actually conclusion, we can say that k is equal to 6. So at the beginning I calculate the value of k. So this is the value for the k for this function. At the second part, they ask you to calculate the probability of x between 0.4 and 1. To calculate that one, we should calculate the value of a function when the limit of integral is given by 0.4 and 1. Means that this is as the same as probability of x is probability of x between 0.4 and 1. Means that this value based on the condition of a probability. If you remember that the third condition said that this probability can be calculated by this one, and if you calculate the integral you can find the value of the probability, which is equal to 0.332. So at the end they ask you to find the probability distribution, cumulative distribution function. Before that we calculate the cumulative distribution function, I want to sketch the function as well. So I sketch the function over here. You can see the function. The given function is defined as one parabola between 0 and 1. As you can see over here, there is a parabola between 0 and 1. To sketch the function, it only needs to put the value of 0 and 1 inside of the function. So the given function is 6x times 1 minus x, which is equal to 6x minus 6x squared. And as you can see, it's a second degree polynomial, or it's a parabola. So if you put 0 at that point, then f at the point 0 is equal to 0, and at the point 1 as well, if you put 1, it will be 6 minus 6, the result will be 0. So in both of them we have 0, and because it's a parabola and we found their x-intercept, so the shape of the function will be something like this, and the area under the curve of course should be equal to 1, which is equal to 1, of course, means that the area under the curve is equal to 1. So this is the shape of a function, and the remaining parts are 0. For the elsewhere we have 0, there is nothing over here, means that it's 0. It's totally as the same as horizontal line. So for calculating f of x, or the cumulative distribution function, we calculate it in 3 cases. So if you can see, first of all we calculate it when x is less than equal to 0. If x is less than equal to 0, means that x is located somewhere here, that I denoted by the yellow color, and the area under the curve from very beginning, from minus infinity up to the x, is equal to 0. Because the function, based on a definition, the cumulative distribution function is an integral from minus infinity up to x of ft dt, and the function for the value less than 0, x is less than 0. So for the value that x is equal to 0, the value of the function is defined as a 0. It's a part that contained in elsewhere. So that integral is equal to 0 because the function is 0. So for x less than 0, the value of the function is equal to 0. Right now, if x is somewhere located somewhere between 0 and 1, for example, x located at this point, then as you can see over here, the area under the curve contains all the value between minus infinity up to 0, and this part that I just shaded over here means that this part also included for the value of f of x. So again, the formula is as the same, means that f of x, or the cumulative distribution function, is the integral of ft dt from minus infinity up to x. But I divide it to 2 parts, one from minus infinity up to 0, then from 0 up to x. I can do it because the value of the x is between 0 and 1, means that x is greater than 0. I can split it like this to 2 parts. From minus infinity up to 0, the value of the function is 0, so the integral also will be 0. But for the values between 0 and x, the function is given by 6x minus 6x squared. So I'll just write it over here, 6t minus 6t squared, because the differentiation is t dt, so I will write it as a 6t minus 6t squared, and I take an integral from 0 up to x. The integral of 6t will be 6t squared over 2, and 6 over 2 is as the same as 3. And the integral of 6t squared will be 6 over 3t cubed. So if I just substitute x instead of the t, then I subtract it when I substitute 0 instead of the t, then the result is 3x squared minus 2x cubed that I wrote it over here. So for the last condition also, where x is greater than 1, by calculating f of x, you can see the integral. Indeed, if x is located over here greater than 1, then all the probability that is covered previously contains this parabola as well, and this parabola, the area under the curve for the parabola is equal to 1. So the value of the cumulative distribution function at the point x will be equal to 1. So this is the value of cumulative function where x is greater than equal to 1. I will finish our lecture today and we will continue our discussion for tomorrow. Thank you.